Hello everybody. So today we're going to have a look at Einstein's photoelectric law and the calculations that are involved with that. And before we do, we'll just have a quick recap of what the photoelectric effect itself is, so that we're in a better place then to discuss the maths behind it. So the photoelectric effect is what we observe when we shine light rays or any other electromagnetic radiation of a high enough frequency onto a metal. What we notice is if the frequency and energy is high enough, that electrons are then emitted from the metal. This is called the photoelectric effect. Photo meaning light rays, and then electric to do with the electrons being released. Now, we mentioned before that these light rays or electromagnetic radiation have to be of a high enough frequency or energy, and that's because the energy of any wave of radiation is going to be proportional to the frequency. So those two things are related, and they're related using this formula here. The energy is equal to h times the frequency. So energy is proportional to frequency, and a h then is just a constant called Planck's constant. I'll write Planck's constant up here at the top. 6.622 by 10 to the power of minus 34 joule seconds. So you'll find that in the table of constants in your log tables. Normally around page 46, page 47, you'll see all the constants. Now, these terms here are energy needed to release the electrons and the frequency of radiation is needed for this to happen also. And they have specific terms. So the energy needed is called the work function. It's the amount of energy you need in order to be able to release an electron from the metal. And F here, the frequency needed to start photoelectric emission in the metal, is called the threshold frequency. So anything past that threshold frequency or past the work function will start allowing those electrons to be released. And the reason why this whole concept is so important is because it allowed Einstein to come up with his idea of wave-particle duality, basically saying that according to the results of this kind of an experiment, it looks like light rays and other electromagnetic radiation behave as a particle, with individual little packets of energy being transferred to electrons. We already know about Thomas Young's double slit experiment, where he had two slits in a aperture like this, and what was seen was something like you'd expect to see from a wave, whereby wave crests come in, they diffract through the first aperture, and then we see them creating an interference pattern through the second one, with lots of different points of constructive and destructive interference. That's a pretty rough sketch, but hopefully it is enough to jog your memory. So Einstein was not disagreeing with this. He said that that experiment was still valid and it did still show that light behaved as a wave. He was just saying that it appears as a particle too, which is why we call it wave-particle duality. Dual, I'm sure we all might be aware at this point, means related to two things. So it's both things at the same time. Einstein's photoelectric law basically just said that once the amount of energy being transferred in each of these photons or packets of energy exceeded the work function, then any remaining energy will be used as kinetic energy to make those electrons exit faster. So if we want to represent this mathematically, we would say that the energy that's being brought into the electron is going to equal to the work function. So a certain amount of that energy is going to be used to release the electrons, and then anything else that's left over is going to be added to the electron as kinetic energy. This whole equation here really ties into the idea of conservation of energy. The energy can't be created or destroyed, only changed from one form to another. So the energy that comes in on a photon, some of it is going to be used to free the electron from the atom that's a part of, and the remainder then is going to stay in the electron as kinetic energy, giving the particle a velocity. So this formula as it is pretty straightforward. Where it becomes a little bit more complex is that we have individual formulas for each of these that we might be asked to use to sub in and find the value for the work function, for example, or for the kinetic energy afterwards. So I'm going to go through each of those formulas now. So the first one that we'll look at here is for the far left hand side. The energy of a photon, we can say, is equal to H times F. So F is the frequency of the radiation coming in, and E is the energy that's just included in each of those individual photons. Again, they're held together by that Planck's constant H, which we've already gone through there. But you can again find it in your log tables, page 46, page 47. Our work function has a very similar formula. The work function just tells us how much is the minimum amount of energy that needs to be there in order to free these electrons from the metal. So the work function, the minimum amount of energy, is going to correspond to the minimum frequency of radiation that can be used, what we call the threshold frequency. So this formula looks very similar because it is basically the same formula, just repurposed with some of the variables looking a bit different. Phi, or the work function, is again an amount of energy, and then F naught over here on the right hand side is just the threshold frequency. So again, it is just a frequency, but it's the minimum one. Now you might be wondering what's the difference between these. On the left hand side, their energy that's coming in from the photon is the total amount of energy that's going to be given to the electron. Our work function is just the amount of energy that's going to be used to release the electron from the metal. If this was the same as this, the energy coming in from the radiation was the same as the work function, well then the electron will be freed, but there would be no kinetic energy left to give it a velocity. So this brings us down to talking about the kinetic energy formula. This is a fairly old formula that we've already seen in 5th year during our study of mechanics. So kinetic energy, as always, equal to a half times the mass times the object's velocity squared. Because we're dealing with electrons, the mass is going to be more or less a constant, which again can be found in the log tables, page 46, page 47, with the rest of the constants. So really what we're concerned about here more so is that it allows us to transfer between kinetic energy and the maximum velocity of the electron. One other formula that I think it's important to be aware of here is the relationship between the frequency and wavelength of any radiation. So that formula is C is equal to F times lambda. Speed of the radiation is going to be equal to its frequency times its wavelength. So this will just be handy in case they give you any wavelengths to deal with. It'll allow you to transfer it back to frequencies before you put them in here. Our wave speed here, C, might sometimes be the speed of light, because we'd be dealing with visible light, but actually for any form of electromagnetic radiation, the wave speed is going to be the exact same, 3 by 10 to the power of 8 meters per second. So that makes it easy enough to remember. We'll label that there as our bonus formula, just in case it might come in handy for you while you're doing some questions. So now we'll have a look at actually answering some of these questions. So we'll start off with this question here. They tell us that a metal has a work function of 1.210 by 10 to the power of minus 18 joules. A photon falls on this metal, which has a frequency of 4.528 by 10 to the power of 15 hertz. So the first thing they want to know is, will an electron be emitted? Well, we know that the work function is 1.210 by 10 to the power of minus 18 joules. In order for the electron to be emitted, the photon has to have an energy greater than the work function. So there's two options here to how we can answer this question. One of them is to look at the work function and convert it to a threshold frequency. Using our formula, work function is equal to Planck's constant times the threshold frequency. This will give us the corresponding frequency that needs to be overcome in order for an electron to be emitted. And we could then compare this to the frequency of the photon. If the frequency of the incoming photon is greater than the threshold frequency, then our electron will be emitted. The second way, which is what we're going to do now, is going to involve us looking at the frequency of the incoming photon. We will then try and convert this to energy. So we'll know what the energy of the incoming photon is. If the energy of the incoming photon is greater than the work function, then we know that the electron will be emitted. So to convert this frequency to energy, what we're going to do is use this formula. H times the frequency will give us the total energy. This we can say is our energy coming in from the photon. When we sub in the quantities we know, we end up with two brackets that look like this, and then we can use our calculator to multiply them out. When we multiply this out, we get the energy of the photon as 3.000 by 10 to the power of minus 18 joules. Now, if we want to see if an electron will be emitted, we compare the energy from the photon to the work function, and if the energy is greater than the work function, then an electron will be emitted. So 3 by 10 to the power of 18 is greater than 1.210 by 10 to the power of minus 18. So that means that the work function has been exceeded, so an electron will be emitted. I deliberately chose the first example where the two powers will be the same, because then it just means the bigger number here is going to represent the bigger number overall. Sometimes you might be faced with a situation where they have different powers. So for example, 10 to the power of 18 will be greater than 10 to the power of 16, regardless of what the number in front is, as long as it's standard scientific notation, with a number that's between 1 and 10. Similarly, if you go to really small numbers, anything by 10 to the power of minus 16, for example, will be a bigger number than something by 10 to the power of minus 19. So a good guide is first of all to look at the powers of 10 to see if it's exceeded the work function, and failing that, then we just look at the numbers here and compare them. We'll move back now to part B. So we already know that yes, it will be emitted, and our reasoning why is because the energy in the photon exceeds the work function. So for part B, we'll start off with a clear slate again, and we are asked what the electron's maximum kinetic energy would be. So now we're really getting into Einstein's photoelectric law and using that equation. So the energy in should be equal to the work function plus the kinetic energy. Or if we want to rearrange this, we'll get that the kinetic energy is equal to the energy of the incoming photon take away the work function. This formula makes sense because the kinetic energy will be what's left over when we take away the work function from the energy of the incoming photon. When we fill in the value for the energy of the photon and the work function, it should look like this, and now we can solve this by just putting that equation into our calculator. It's important that when you put it into your calculator with our scientific notation that we include terms in their own set of brackets, so that the calculator doesn't get carried away and start carrying out business that we don't want it to do. When we follow it through to our answer, it will give us an overall result of 1.79 by 10 to the power of minus 18. this is a measurement of energy, so we're going to include our unit joules. So this provides us with an answer to part B. We'll start again with a clean slate now. I'm trying to calculate the velocity for part C. So for part C, we're going back to our more basic mechanics formulae. We're going to use the formula for kinetic energy that we learned in 5th year. The kinetic energy of an object is a half times the mass times the velocity squared. And now we can start filling in what we know. We've just calculated the kinetic energy. We know the mass of the object because we're talking about electrons, so that can be found on page 47 of your log tables. And then that leaves us with one unknown variable here, the velocity, which is what we're trying to solve for. So when we fill in the values we know, our kinetic energy is 1.79 by 10 to the minus 18, and our mass is 9.109 by 10 to the power minus 31. And we can start multiplying this out now. Starting over the right hand side, it simplifies to 4.555 by 10 to the power of minus 31. And now we'll just divide both sides by that number to get v squared by itself. So dividing the left hand side by 4.555 by 10 to the minus 31 gives us 2.613 by 10 to the power of minus 12. And now finally, to get v by itself, we're going to square root both sides, giving us v, the velocity on the right hand side, and 1.616 by 10 to the power of 6 on the left hand side. This then is our final value for the maximum velocity of that electron after it's emitted. 1.616 by 10 to the power of 6. And now we should always be checking that we've included our unit. So for velocity, that'll be meters per second. So we'll have a look at the second question now. This question talks to us about a photocell that has a work function of 1.5 electron volts. They say if the light of wavelength 285 nanometers falls on the cathode, what is the maximum kinetic energy of the emitted electrons? So talking about light waves falling on a photocell, we know that's probably going to be a question about the photoelectric effect. So we'll write out Einstein's photoelectric law. So that'll take us already pretty close to solving out this equation. We know that the energy from an incoming photon will equal to the work function plus the kinetic energy of the emitted electron. What we want to do to answer this question is get to here EK, where we can figure out the actual kinetic energy that that electron is going to have. Now, I've chosen this particular example because there's two common tricks they can use to try and catch you out here. One of them is that they give the work function in electron volts, when this formula only works when the work function is inputted in joules. So we'll have to convert from electron volts to joules before we can fill in the work function. A second trick they've used is telling us the wavelength of the incoming electromagnetic radiation instead of telling us its frequency or even its energy, which would both be easier ways to fill it into the formula. So we're going to have to use our bonus equation there from earlier on to convert it to frequency first and then find out the energy of the individual photons before we can sub it into our photoelectric law. So we're going to start off by dealing with the electron volts and finding out the work function in joules. So a good place to go will be our table of constants on page 46 of the log tables. This tells us that 1 electron volt is equal to 1.602 by 10 to the power of 19 joules. So if we want to find out what 1.5 electron volts would be, we'll multiply both sides here by 1.5. This will keep the ratio the same, but will let us know what 1.5 electron volts is in joules. So multiplying the left hand side, we get 1.5 electron volts, which is what we were after. Multiplying the right hand side, we get 2.403 by 10 to the power of 19 joules. So at this point, we now have the work function in joules, and that'll be ready to fill into the photoelectric law. Unfortunately, we still need to figure out what the energy of an incoming photon will be first of all, before we can proceed and then start trying to figure out the kinetic energy. So we'll write out our formula for the incoming photon and its energy. We know that we can figure it out using Planck's constant, that the energy of an incoming photon will be Planck's constant times its frequency. Unfortunately, like I mentioned, they've done an extra step of trying to trick us, and they've given us the wavelength instead of the frequency. So we need to first convert from wavelength to frequency and then fill frequency into this formula. So this ties back to the bonus formula I mentioned earlier on. The wave speed is equal to the frequency times the wavelength. This formula is hopefully something we're familiar with from when we covered the topic of sound already and other types of wave. If we rearrange this formula for frequency, we get frequency is equal to the wave speed divided by the wavelength. And now we know that for all electromagnetic radiation, wave speed is the same. So 3 by 10 to the power of 8 meters per second. And we're given the wavelength here as 285 nanometers. Nano, in case you don't remember, is a prefix that means 10 to the power of -9. If you're ever unsure about the meaning of any of these particular prefixes, you can look them up on page 45 of your log tables. They're all there. When we run this calculation through, we find that the incoming electromagnetic radiation has a frequency of 1.053 by 10 to the power of 15 hertz. Now we're in a position where we can put it into our formula for the energy of the photon using Planck's constant. So we'll sub that in here, and that will work out to give us a total energy for the incoming photon of 6.977 by 10 to the power of 19, which we now know in joules. At this point, we can go back to the photoelectric law. And now we're in a position to fill in the energy of our incoming photon, which we now have in joules, our work function, which we also now have in joules, and that will allow us to solve out our maximum kinetic energy. So we'll rearrange the formula first, giving us the kinetic energy is equal to the incoming energy take away the work function. This gives us a final value for kinetic energy of 4.574 by 10 to the power of -19 joules. Again, the reason why I chose to do one that has so many parts in it is just to give you guys an idea of how to break down the different tricks that go into solving this formula. But not necessarily to overwhelm you. I want you to keep in mind when you're going through a question like this, that for every individual part of this question you get right, you're going to be getting marks in the leaving cert. So even converting from electron volts to joules, for our work function, that would get you marks. Writing out the photoelectric law will get you marks. Writing out the wave speed formula will get you marks, and also any of these other formulas here, as well as calculating frequency, etc. So there's plenty of marks on offer for any question this big. So make sure that you're not becoming overwhelmed and writing it off without thinking about what individual parts you might be able to do, which could end up being enough to give you 60 to 70% of the marks before you even get to solving out the actual answer.